Hello. In this video, we are going to go through the basic operational layout of EaRL and the features in the software that can be used while defining a new project. So this is essentially a general introduction of EaRL's main console that we see over here and its features. So right now, after I opened EaRL at this moment, we are still waiting to define a new project so that all the buttons that we see in the main console would be activated. So just for the purpose of this introduction, I will open an existing template project so that all the buttons become activated. So let's start from the top essentially, and again, this interface or this main console has intuitive layout. So from the top, going downwards, this essentially constitutes the basic steps of defining a new project. All the way at the top, so here you can see the version or the current version of the installed EaRL. So this is right now we are at version 1, the beta release. Next, this is the button for registering to receive any future updates from EaRL. So since this is the beta version, there will be a continuous update to EaRL's functionalities and to fix some bugs that may arise for some users. So in order to get the latest updates and receive the latest compiled executables, so you are recommended as a user of the program to register. By clicking here, you will be prompted to this web page over here where you can register your name, your email, and your affiliation, and essentially any updates you will receive them right away by email. Next, there are like some other buttons. This is the About button that gives some basic information regarding EaRL. What does it do, how to cite the software if you use it, and some other references. The help, this will open the EaRL manual, which is already actually downloadable with the supporting documents, so you can open it either way, directly from your computer or from the console. The developers button, so this button essentially opens a new interface that display the layout or the code hierarchy or the code tree of the program, and essentially it lists all the functions and graphical user interface that are used in EaRL, so that they can be referred to when you are trying to, as a developer, when you're trying to modify the code. This will be explained in more details in a later video. Again, you can see all the variables defined in EaRL's code, and by clicking on any one, you can see what does this variable means and where is it used and so on. The next below this is the main panel, or what we call it panel A. So this is the file management panel where you can start a new project using the button new. You can open an existing project using open, like I just did in the beginning, where you can save the current project under a new name, save as, and then the scope. And the scope essentially it opens a summary of the current project definition that you have right here. So if I click this right now, it essentially shows me this. How did I define the building data, all the parameters, how did I define the components inside the building, the response data, the seismic hazard, and all other things related to any typical project definition. So this is the file management panel. Below that, you have this second panel over here, and this is essentially panel B, which contains a total of 4 buttons, which are the main or the basic components of any project definition to conduct a loss assessment analysis. So the first one would be to define the building data. So in this one, if I open it quickly, essentially you will need to define some basic properties of your building. You can give it some kind of text description over here. You can say that I'm doing analysis of a steel office building or something like that with some kind of structure system. You can write anything as a description. You can specify the occupancy of the building. So there are different types of occupancy, and this will dictate how much population inside the building essentially. You can also define some other things like the construction material, the structure system used in the building. So these are all optional definitions that help with the later steps in the project definition to make it much easier. You define some geometric attributes like the number of stories, the footprint area, the total area. And then you define other things as well, like the replacement cost, which is the cost to replace the building and rebuild it. The demolition cost, if you need to demolish the building, how much would this cost in $1 million, and so on. So this would be the first thing to define essentially the building data. So after defining the building data, the second step would be to define the component data. Essentially what this means, you will need to define all the building's components and contents. So this includes the structure components, the non-structure components, and any type of contents inside the building, like furniture or any type of equipment in that sense. So structure component could be like the type of columns used, the type of connections, the type of beams, the type of slabs, and so on. Non-structure components will be like partition walls, curtain walls, suspended ceilings, and others. When it comes to contents, again, this is like furniture, like shelves, desks, computers, and etc. So these are all need to be defined here in the component data. If I open this option, you will see that you have 3 options actually to define this. You can define this manually, and this would be the laborious but more high resolution way of doing things, where you essentially specify manually the type and the number of each building component or content at each story or floor. So this option actually can be done or can be simplified through an interactive interface that we have in EaRL, and you can also use some import option to import this data, so to have it stored, pre-stored into an Excel file and importing it into EaRL. The second option, and the third option as well, this is to use a more implicit approach, where you essentially define, use existing what we call a loss EDP or story loss functions that are available in literature. So currently we have 2 of those actually implemented. There are these ones that were developed for steel buildings, and by clicking here on this link, you will go to this actual publication over here that discusses the parameters and the assumptions and how these loss EDP functions were developed. So essentially these functions directly relates the loss, which would be the repair cost in this case, with the engineering demand parameters. So in this case, you don't need to define explicitly the building contents. There is also another set of loss EDP functions. So these ones over here, again, there is a link for the publication. So in this one, you essentially, this one were developed for RC buildings. And in any of those two, you will need to specify just a limited number of basic parameters to use them. So for sure, they are much more convenient than the manual definition. But of course, they might be less accurate than the high resolution or the explicit approach of doing a manual definition. Let me go inside each one of those just to give you an idea of what you can do. So if I go to the manual definition, so if I look at this interface that I have here for the manual definition, you can see here from the top that you can use these drop-down menus to select the different category of the component. And by selecting a given category, then you will get the list of subcategories, essentially, or the components under this category, where you can select from all of them. So these are all the components that are available from FEMA P58 component database that's implemented here. So these are the ones that we see over here. And essentially by selecting one of these components, you can select the floor or the story location. So for instance, if it's a given story, you can say this is the first story, second story, third story, or whatever, or it's if this component is at a typical story. And then you need to insert the number of units that are available at any given level. And then by doing add entry, you can add this and it will be listed into this table that we see over here. And after defining this for each component at each floor, then this can be submitted to the to EaRL directly. Now, essentially, an easier way. Let me first clear the table right now because I have already some defined here. So right now you see there is nothing. So for instance, if I define as the superstructure, for instance, and if I go at the top, maybe I will use bolted shear tab gravity connections that are present at each floor, each typical floor, and at each floor I have, let's say, 50 units. And then I can say add entry, and then automatically you will get this component added to your component list. And here you can see all the basic parameters like the component name, the index or the ID from the component fragility data. Again, all these components are the one available from the fragility, from FEMA P58 fragility database that has over 776 components that you can choose from. Now, you can do this for each specific component using the drop-down menu that you have over here, but this might be a bit, it might not be very convenient. It might take a long time depending on how tall is your building or how many components are available in your building. So an easier way would be to use the supporting documents and to define these components in an Excel file that can be imported into this module. So let me show you here. Last time we said that you download from the EaRL repository, you can download the supporting documents. Inside you will see a number of supporting files and folders. If I open this template component data, so essentially in this one, this is an Excel file that has this sheet that's called component data, and it has the other sheet that's called database. If I click on the database, you can see here all the different, what we said, like 700 and something components from FEMA P58 already listed here, like the basic parameters of these components that you can choose from. And over here in this sheet, the component data, all you need to do is to specify the ID number and the level, floor or story, and the location, essentially either typical or like specific story or floor, and the number of units. So all this can be done over here. And essentially, like, let me write here, for instance, if I write 1, so automatically you can see here that this one for component ID number 1, this is actually the bolted shear tab gravity connection that we just did in the main interface. But you can do it here, and then you can specify that this is located at the floor. You can say that this is at a typical floor, and then you can say I have like 50 of those. And then you can import this into, again, into the module without using the drop-down menus. Over here in this Excel file, you can see like this is a sample definition for a 4-story building that has different types of components like hydraulic elevators, column splices, wall partitions, suspended ceilings, corrugated slab, fire sprinkler piping, and other things. So it becomes easier now if you do this and you save it and you have it you already have it and you can easily modify it. Going to your main module, you can import the data directly. So going to the location of this template file, that's it. And then it's already loaded into your module, and you can scroll here to check that everything is correct and everything is imported correctly. And then you can click submit, and now it's defined. Using the scope here, you can actually scroll down to the component definition, and you can see a summary of the defined components that you already imported, which are listed over here. So this would be one way of defining the components. The other, we said, like to use these loss EDP functions. If I open, like for instance, one of those, this one for steel buildings, by clicking next. So for this set of loss EDP curves, you will just need to define the type of structure system. So we said this is a steel building. So you have actually 3 types of structure systems: a moment frame, a braced frame with X bracing, a braced frame with chevron bracing. So you can choose whatever one that you want. Then you need to specify the floor area and the total building floor area, and you need to define the luxury level, essentially the contents, how luxurious are the contents, low, medium, and high. Again, if you want to know more details about what each of these levels of luxury means, then you will need to revise, of course, the main publication. And after selecting those, you can submit this, and now this will be used. You can show the loss EDP functions, which will essentially, if you click on this, it will show you the summary of how the loss in dollar relate to the EDP, or the engineering demand parameters in the building. In this case, the story drift ratio, SDR, and the peak floor acceleration over here. Again, these data also are available from the original publication itself. So after defining the building data and the component data, the next step would be to define the response data, which essentially defining the EDP, or the engineering demand parameters. And there are many ways to get these engineering demand parameters. Typically, you would do some kind of numerical model of your building and do some type of nonlinear dynamic analysis in order to obtain this data. and then do the assessment. So actually, if I click on this one, there are 6 options available to define this data to cover all the needs of different users and different engineers. The first one essentially is to define data that are obtained from incremental dynamic analysis procedures. So if you have done incremental dynamic analysis procedure, you can use this option to import your data into EaRL. So again, in this case, the way this is done, it's all done through the supporting documents that are provided with EaRL. So inside the supporting documents, there is actually here, there is this folder that says template response data IDA data. And inside this one, it gives you essentially how the data, the incremental dynamic analysis data, should be organized. So inside this folder, you need to have, just quickly, of course, it is discussed in more details into the manual, but essentially inside this result folder, you need to have individual folder for each ground motion record that you analyzed. Inside each record, you will need to have text files for the peak floor acceleration, the story drift ratio, and any other engineering demand parameters that may be relevant to your project. And inside each one of those text files, you will need to have essentially the IDA data. So in this case, for a 4-story building, I have the data organized in this way. So the first column is the intensity measure, magnitude, and then this would be the SDR, or the story drift ratio, for the first story, the second story, the third story, and the fourth story. So these are essentially the IDA curves that you obtain, but organized into a text file. By organizing this data like this, you can import this into EaRL and proceed with your project. So here again, you have a template data that you can use to organize your personal data. The second option is to, and probably this is like more relevant to typical users, would be to define engineering demand parameters that are obtained from multi-stripe analysis. So multi-stripe analysis, if you are familiar, this is when you have a multiple ground motions and then you scale them at 3 or like a number of different multiple target magnitudes, intensity measure magnitudes, and for each level you will have some kind of values for the engineering demand parameters. So these you will need to import. So this is another option that you can do here. Again, in the supporting document, if you open, this can be organized into an Excel file. So right here, for instance, you have this template response data multiple stripes. If I open this one, you will see over here that if I'm talking about the basic engineering demand parameters, the story drift ratio, SDR, as it's called here in EaRL, and the peak floor acceleration, PFA. So if I want to import this data for, let's say, 3 stripes, so you will need to have different sheets, SDR_1, SDR_2, SDR_3, and in each one of those you have the ground motion number, and then you will have the value of the story drift ratio at each story based on your analysis. So these are all listed here, and this will be imported by EaRL, and then median values will be computed, correlation coefficients, and the standard deviation parameters will be deduced from this data. And again, for the peak floor acceleration at each floor, of course it depends how high is your building. You can also define the same for a number of other engineering demand parameters. Again, this all depends on your project definition. If I go into this just to illustrate this data at multiple stripes, how the module would look like in this case. So if I click next, so essentially we can see here that you will need to browse for the Excel file that contains the data, which in this case I'm using this template Excel file. Automatically, based on the data that you define, the number of ground motions will be updated over here. And then you will need to specify the number of stripes that you want to analyze. So in this case, I'm doing 3. Then you will need to define the intensity level, essentially the values of each stripe. So stripe number 1, this is at 0.301 G. The second one would be 0.6 and 1.1 G, and so on. Again, this depends on your analysis. And then you need to specify the EDP data that you want to import. By default in EaRL, you need always to include the story drift ratio and peak floor acceleration. These are the basic engineering demand parameters. You may want to include other engineering demand parameters depending on, again, your project definition. If you have some kind of component that is dependent, for instance, on the peak floor velocity over here, then maybe you want to import data for peak floor velocity. If you have a shear link, for instance, again, you may want to import data for the link rotation. So right now you have all these different types of engineering demand parameters. You have RDR, which is the residual drift ratio, VRD, the vertical residual deformation, the damageable wall drift, the beam rotation, column rotation, link rotation, the peak floor velocity, the effective drift, the racking drift. So these are all like basic engineering demand parameters that they typically come up in literature, and most people are using them. If you have a different type of engineering demand parameters, then you can use these generic story-based or floor-based demand parameters to define something new. And then again, by submitting this, then that's it, you submit the data, it will be imported into EaRL. Again, when it comes to the response data, there are again different types. So you can also import data from essentially, again, number of ground motion records that are scaled at a single intensity. So this is very, very similar to the multiple stripe analysis, but in this case, you have a single stripe. So again, if you look into the supporting data folder, you will see again another Excel sheet template that you can use or refer to when defining your data. You can also import directly, instead of having the explicit EDP values from each ground motion, you can directly provide the parameters. So essentially, you will need to provide the median value of the EDP and the dispersion of this value at each level. So in this case, again, there is a template for this, the one that's called template response data parameters. If I open this one, you can see that, for instance, here for story drift ratio, you will just need to define the median story drift ratio at each story and the sigma of the story drift ratio or the logarithmic values of the story drift ratio over here. So using those two parameters, EaRL will automatically build the log normal distribution of the EDPs and continue with the computation. You will also need to define the correlation between the logarithmic SDR values as you see over here. So again, you will need to define this for each of the engineering demand parameters of interest that you want to import into EaRL. And again, submit this to do the analysis. So the first four options that we went through, they are all deal with importing data. So essentially, it's up to the user to do the nonlinear analysis and then organize the data into Excel files and then importing them into EaRL. The last two options are essentially to generate without the need of a nonlinear model, which might take time, as we all know, is to actually generate the data using simplified methods. So the first option here is to actually run a nonlinear multi-degree of freedom shear model, or what we call a stick model. And from this, you will run this nonlinear analysis, which will actually use the OpenSea's engine to run it and deduce the data from this model. The last option is to actually use the FEMA P58 simplified analysis method, again, which uses a linear elastic shear model again, which is analyzed again in OpenSeas, and then the linear EDP values are corrected using some regression equations to account for the nonlinear behavior. If I open, for instance, this option, like using a multi-degree of freedom shear model, so you can see here that you will need to define the system property. So essentially, this is the response of your building at each story. Do you want it to be an elastic? You want it to be bilinear? You want it to use the IMK or the Ibarra-Medina-Caravincler bilinear model, or the Ibarra-Medina-Caravincler peak-oriented model. Again, if any of you are familiar with OpenSeas or ran things in OpenSeas and deteriorating component models, then you are for sure you are familiar with these two models. So these are models that incorporate cyclic deterioration in strength and stiffness that you can use here to represent an entire behavior of a story in this case. And then you will need to import the properties defining the elastic or the bilinear or the peak-oriented behavior, whatever it is, from Excel. Again, this can be done from the template Excel file shown here. So if I open this one, a template MDUF shear model, for instance, so you will need to define the story heights. So these are all parameters that are needed to build this multi-degree of freedom system. You will need to define the story height, the load, gravity load at each floor, the mass at each floor, and then depending on your definition of the story behavior, for instance, if you are using a bilinear behavior, a simple bilinear behavior, then you will need to specify the elastic stiffness and the lateral force, the lateral yield force, and the strain hardening slope, essentially in this case. If you go to the more sophisticated nonlinear deteriorating models, then for sure there will be like more parameters that you need to define, and these are all explained in the manual. So these can all be imported over here. So for instance, if I say bilinear and I go to the supporting documents and import this Excel sheet, so now it's been imported. You also are going to do some kind of nonlinear analysis on this multi-degree of freedom model. So you will need some ground motion records to run the analysis. So again, you can browse for the folder that's containing these ground motion records. So again, you have here in the supporting data these sample of ground motion records. Actually, these are the ones that are called the far field set from FEMA P695 that contains like 44 ground motion records. So you can browse for this folder essentially, like as we see here, and we select the folder, and then it automatically detects that there is 44 ground motion records inside, and it imports them. Maybe when you do the analysis, you just want to do the analysis for just 10 record, like subset of these, so you can modify this here. Then you need to specify what type of analysis do you want to do. Do you want to do an incremental dynamic analysis, or do you just want to scale your records for a target intensity measure or a target scale factor? So for instance, if we can use like a target IM, we can say that, okay, scale period, you need to define the scale period, like let's say 0.7 seconds, and the target intensity measure would be, let's say just like 1.2 G, and you need to specify the damping coefficient, let's say 3%. So now, once you define this, you can start by running the model, getting the data, plotting the EDP values after the analysis, and doing this. So this will be actually discussed in more details in a later video where we can go through the whole procedure and see how can we define this type of model. The second option, or the last option, would be to use the FEMA P58 simplified analysis method. And this one is very similar. Again, you will need to define some basic parameters for your system properties. You will need to define, for instance, Vy, which is essentially the shear yield strength of your structure, the drift at which the first yielding occurs, the spectral acceleration at the first mode period, the spectral acceleration at 1 second, the peak ground acceleration, the period of the building, other things related to the ground motion properties and the hazard, so the soil class, the system type, and the ground motion prediction equations for which location essentially in the United States. And then importing again a similar Excel file that has the properties of the elastic multi-degree of freedom system. And after doing this, this can be ran and EDPs can be obtained. Again, this is discussed more into the manual and in FEMA P58 implementation and the methodology documents or reports. You can see more details about this. So again, as we've seen, like in the response data, there is a number of options available, and it makes it much easier and very flexible when it comes to defining the response data. The last part of a definition is the hazard data. And in this case, the seismic hazard data, actually this is optional. And essentially you will need this if you want to compute some time-based decision variables like the expected annual losses, the rates of exceeding some kind of repair cost and such. So you will need the hazard data. So in the hazard data module, you can extract the seismic hazard curve from the USGS hazard maps. So in this case, you will need to provide essentially the longitude and latitude, like the coordinates of your building, the period of your building, and the soil condition. And you will need to browse for the folder containing the raw USGS hazard maps, and these are actually also provided in the supporting material. So this would be this folder over here that you will need to browse for on your PC, and then by clicking submit or plot, this will be extracted. You can also use user-defined hazard curve. So essentially, if you have your hazard data, which is the mean annual frequency of exceedance versus the intensity measure, organized in a text file, then you can import it into EaRL. So in the supporting documents, again, there is a template hazard curve text file shown here that has essentially the data for the hazard curve for the particular project that I'm doing. So you can browse for this document, and then now it's in EaRL, so you can plot the hazard curve, and in this case you will see the scatter of data points that you imported, and they are automatically being fitted with a 4th degree polynomial. So that's it for essentially the basic 4 main component definitions of a given project: the building data, the component data, the response data, and the hazard data. The rest of the definitions are essentially over here in panel C, and these are all the supplementary definitions where you can define further things in your model. Over here you have the damage fragility module, and in this one actually you can explore or edit the component fragility database. So let's say if you define the component data manually and you need to modify some parameters of the fragility data for specific components, then you can do this over here. If you have a new component and you have a new fragility value parameters that you need to define, then you can add a new univariate fragility function or data into the database to use it. You can also add multivariate fragility functions in EaRL. So again, this is something that right now multivariate fragility functions are probably like more accurate than your typical univariate fragility functions. So you might want to define something like this if you have developed such functions for a given component. So you can do this in EaRL. If you have a database, and this is part, again, this has to do a bit with the developers, people interested in developing the program. So you can actually modify the database in MATLAB manually and import the raw data automatically in EaRL. So I will go quickly into like the explore first by the explore editing the fragility database. So if I click next, so you can see here that essentially it automatically here filters the list of components based on the project components that I defined. So you can see here, this is the damage fragility functions for each damage state, for the bolted shear tab gravity connections, and you can see here the log normal or normal CDF functions. You can see the cost associated with each damage state. What does each damage state mean over here? You can scroll to see the distribution of the cost and how does it change with respect to the quantity of components being repaired. You can look at, again, the fragility of the repair time, the embodied CO2 emissions, and the embodied energy, again, the fragility functions. Again, these are all extracted from the FEMA P58 database. You can also check the DS photos. So again, this will show you like some photos of the damaged state. Again, these are all photos from, if they are available, these are all photos from the FEMA P58 metadata. So again, you can look at the different fragility of the different components. You can check how things are deforming. You can check the damage fragilities. Then you can actually edit some of those. If you want to modify some fragility data, then you can click on edit over here, and then you can modify the data right away from here by changing maybe the values of the engineering demand parameters. So from here you can modify for any given damage state for this component. You can modify the description, the controlling engineering demand parameters, the values for the fragility and its dispersion, the values for the cost, for the repair time, again, the casualty and the injury dependency, and all these parameters can all modified here. In the same time, you can, as we mentioned, you can actually add new univariate fragility functions. And in this case, again, similar interface you will see here. So you can add a new component, and then you will need to specify the component name. You will need to specify the description of the damage state. You will need to specify the category of this new component, the controlling EDP, and then you will need to also provide all these parameters and add them to your database, and then you can use them when you are doing your manual definition. So this is the damage fragility module that we discussed over here. Again, it's very versatile and you can do many things with it in an interactive way. The second module is the population model, and this relates to the building data when we define the occupancy. So if I click on the population model, so over here automatically you will see some data that are being populated in these tables and in these fields over here that are based on your definition of the building occupancy. So if I remember when we defined the building occupancy, like for instance, we said commercial building. So there is some kind of population model associated with this occupancy type, and these are all defined in details in the FEMA P58. So for instance, in this case, you have like four people per 1,000 square feet, per area of 1,000 square feet. You can modify this data if you want over here. Again, you have here the variation in this peak population depending on the hour and the day, whether it's a weekday or a weekend. Also the variation with respect to the month. How does it change? You can modify this data if you want directly over here. You can also the population data is essentially used to evaluate the potential number of injuries and the number of casualties that may result from component damage. So in this case, you will need to do some kind of evaluation. So the evaluation time during the Monte Carlo simulation process of FEMA P58, you can modify this whether to make it random time, so it can be assessed randomly on different times, or you can actually define a specific day or a specific month where you want this data to be assessed. You can actually visualize this data that's tabulated over here by clicking visualize, and in this case you can see again these variations that we discussed, and occupancy type and everything, which again you can modify. So the after the population model, you can also define the repair time scheme, and if I click on this one, from this module essentially you can specify what kind of repair time scheme are you going to use. So there are three basic ones, essentially sequential, meaning that each component type will be repaired in a sequential manner. So for instance, you will repair columns first, then you are going to repair the beams, then you are going to repair the partition walls, then you are going to repair the suspended ceilings, then you are going to repair the heating and ventilation equipment, and so on and so on. So sequential, of course, this means that it will take more time to repair things inside the building. Then you can select simultaneous all components, where essentially everything, all the damaged components inside the building will be repaired in the same time. So this, of course, will reduce the downtime or the direct downtime due to repairs inside the building. You can also select simultaneous component groups. So basically you can say that, all right, for let's say columns and beams, these will be repaired in parallel, simultaneously in the same time. Then this will be followed by the suspended ceiling at the partition walls. These will be repaired in the same time. Then this will be followed by the plumbing and the heating equipment in the same time, or the electrical equipment. So again, these are the three basic categories that you can select here, and based on those you can define or provide in here in this table the IDs of the components that will be repaired simultaneously. So for instance, here when I select simultaneous all components, automatically you just have one row that includes all the IDs of the component data that I already defined. So everything will be repaired simultaneously. If I do sequential, then each component ID is in a different row. So this means that each one will be conducted individually, and this will be in series. If you do simultaneous component group, then you will need to say, for instance, component ID number 1 and component ID number 87 will be repaired together, and then component number 341, let's say, and 667, and component number 712, this will be again together, and so on and so on. You can also specify if the units of the same component at a given story floor will be repaired in parallel. Again, this is something important. So if I'm doing repairs at a given story, let's say I have beams that have yielded and I'm doing the repairs at a given story or floor, am I going to repair all these beams or these units in the same time, or in series again? So you can specify how this will take place. Again, repairs are going to be conducted at different stories or floors simultaneously, or it will be done at each story in series. So again, you can select this. So this will affect the clearly the repair time, or the repair time consequences of the damage. So if we proceed with the next option, which is the demolition, defining the demolition fragility. So in this option, we are essentially trying to tell EaRL, or in the loss analysis, how what's the potential of demolishing, or what's the probability of demolishing the building given the residual drifts in the building. So you have three options essentially. The first one would be to not to consider demolition, that regardless of whatever residual drift, don't consider the demolition event. Or you can say that, okay, I will define the demolition fragility based on univariate fragility functions that is dependent on the lateral residual drift ratio. And in this case, you will need to define the distribution parameters of this fragility curve, which is essentially the median value and the dispersion or beta value of the log normal cumulative distribution function. If here, for instance, if I use 1% radian and 0.3, if I click on plot fragility curve, so here is how it will look like. Again, you can modify these values depending on how conservative you are. The third option is to use a bivariate demolition fragility function, and this is the state-of-the-art or the updated methodology, which considers both the lateral residual drifts and at the same time the vertical residual drifts. So, which may happen in your building, that you may have large vertical residual drifts but small lateral residual drifts, and in this case the former, which is the VRD or the vertical residual drift, will control the demolition potential. This is a link to this publication that discusses how can you define such fragility function, which essentially you will need again the distribution parameters, the median and the dispersion for each EDP, the lateral residual drift and the vertical residual drift. Right now you can see that this option is not actually active, and the reason for that is that when we define the response data, we didn't import response data for the vertical residual deformation. So in this case, there is no sense of defining a bivariate demolition fragility function. But in the case that you have already defined or imported the data, the response data for the vertical residual deformation, then this will be active, and then you can actually define a bivariate demolition fragility function. Similarly, you have another option for the collapse fragility, and by clicking on this one, again, there is a number of options, 4 options to be specific. Again, you can ignore that collapse will take place, that ignore the collapse event altogether. The second option would be to deduce the collapse fragility function or the collapse fragility curve from IDA data. So data from incremental dynamic analysis. Since incremental dynamic analysis, you incrementally analyze your building up to collapse typically, so you can deduce the collapse fragility directly from this. But since we didn't define in this example, we didn't define IDA data, so this option is not available. But had it been available, then you will need to just provide what story drift ratio limit at which collapse can be considered to occur, which typical value would be 10% radian or 15% radian. Again, this is up to the user. If you don't have incremental dynamic analysis, you can specify directly the parameters of the collapse fragility curve, that is the median and dispersion values. The median will be, in this case, the median of the intensity measure, or in our case, the spectral acceleration in units of g. Or you can specify this rather than the median. You can specify a point on the curve. So for instance, if you already know that the probability of collapse is 4% at 0.45 G, and given the beta values, then using this data, the collapse fragility curve can be constructed. You can plot, click on this button to plot the fragility curve, which you can see here. This is the point that we specified, and then from this you can see what would be the median, the actual median value associated with this. The last thing, which is the last option, supplementary option you have here, is to control the IM, the intensity measure, and the EDP ranges and bins. But in this option, actually, if you click on it, so depending on how you define your project, you can control the ranges for the intensity measures, for integration accuracy. Those are mostly relevant if you are doing analysis using the peer methodology, not the FEMA P58. The EDP pins, again, you can use the default values, or if you want to specify the specific ranges, so for instance, for drifts and rotations, you want the range to be from 0 to 0.3 radian, let's say, with an increment of 0.01% radian. Again, ideally, you don't need to play with these values and just use the default values unless it's necessary and you want some like a more accurate computation. So you can play with these values over here. But in general, I will leave right here those as they are. So now that we covered the basic project definitions panel and the supplementary project definitions, the last thing is these three buttons in this panel over here, the fourth panel, or panel D. So this one where you can conduct the computation, and after the computation you can visualize the data or you can report the data in text files. For the computation, if I click on this one, as we mentioned, there are basically two types of methodologies implemented in EaRL. You can do the original peer methodology, and in this case you will just need to specify what kind of cost values to be used, whether it's the median or 90 percentile or 10 percentile values. That's it. If you are using the FEMA P58 methodology, which is the state-of-the-art methodology, in this case you will need to define the number of simulated structure responses, or what we call realizations. So that typically you can use like 500 or 1000 realizations depending. You can also specify additional uncertainty to account for modeling uncertainty. So you can identify this additional parameter that will add more dispersion to the imported EDP data. So you can, for instance, use like 0.1 additional uncertainty. You can check this box if you want to also compute the potential of issuing an unsafe placard to your building, depending on the extent of damage. And after defining those and specifying the methodology that you're using, then just by clicking run, analysis will be conducted. So if I click run, for instance, so you can see here in this this is the data status that shows essentially what's happening. So right now it's computing the repair loss. This is a progress bar that can show you where you're at. So right now you are at stripe number 1, doing the 500 realization. Now you're moving to stripe number 2. So now estimating the casualties and injuries and saving the lost data, and it's done. So typically most projects, it will take less than a minute to run the analysis. After the analysis is done, then you can visualize and report the data as we discussed. So for the visualization module, if I click on visualize, so you will get this interface, which essentially all the options for plotting the results, and these will change depending on the methodology that we use. So right now we use the FEMA P58, so you can plot multiple things. You can plot the scatter of the repair cost or the repair time versus the realization number. You can plot the loss breakdown by event, so essentially how much would be the repair cost, for instance, with respect to the collapse, demolition, structural component, non-structural components, and such. You can see the distribution of the consequences, the repair cost and repair time, along the building height, and you can see this deaggregated by the component type or by the component name. You can also see time-based decision variables or consequences like the annual exceedance of repair cost, and this is now available because we define the hazard data. If you want to see just a summary, so then you have the summary plots over here, which essentially will show you an interactive interface that has all the data. You can also define, if you want to see the loss units, these are the cost loss units, as an absolute value like in dollars, or as a normalized as a percentage of the replacement cost of the building. And you can extract this data also for a specific realization number or a specific analysis stripe. If you go to the summary plots, just to give you an idea, so the summary plot that you see here, again, you have different tabs, each of which will show like a set of plots. From here, you can control which stripe you are looking at. You can select from this slider the number of realization. So right now we are stripe 1. You can see here that for the 500 realization, the median and mean values of the repair cost, it's around $0.07 million. You can see the distribution here, the histogram. You can convert this into a CDF to see the mean and standard deviation of this repair cost value. You can see the distribution of the repair cost with respect to the building height. Again, you can move to other stripes. So again, if I move to higher stripes, you will get larger losses. So you can move here. You can exchange between different realization, and you will see the distribution here. If you move between the different tabs, here you can see again the deaggregated repair cost with respect to the component type. And I can see here, like for instance, that the corrugated slab is the one that's contributing most to the damage, followed by the wall partitions and the hydraulic elevator. You can see here the collapse probability at stripe number 2 and the demolition probability. There are no injuries or casualties in this case. Had been we checked for the unsafe placard, then you will get the probability of issuing an unsafe placard in this case. You can look at the repair time again, so you can see how much time at stripe number 2 for a given realization. So you can see here that you have here, for instance, a mean of 12.4 days repair time in this case. If you move to larger stripes, you can get larger values. Like for instance, here I will get more than a month of repair time. You can also investigate the the EDP distribution. So these are the generated EDP values at different stories. for each realization, so you can check these values. So at stripe 3, the median story drift ratio at the third floor, for instance, is around 4% radian. If you go to the second stripe, this is about 1%. So you can investigate all this data for the peak floor acceleration and other engineering demand parameters that you defined in your project. All the data that you have here shown in these plots can be saved to text files by clicking on this button and specifying the directory where you want to save the data. So you can see from these summary plots, essentially in this interactive way, you can explore everything happening for the different consequences in one place. Finally, for the reporting, again, you can do, instead of visualizing, if you want to report this directly as text files so that you can process the data later on. So again, you have a similar module here that you can specify what kind of data that you want to save, repair cost, repair time versus realization, the project definition summary, the breakdown by component name, the repair profile. All this can be selected and saved as text file as XY data. At the same time, you can save the raw data, which is essentially, this will be the full deaggregated data for each realization, and this will be provided in a .mat file that, if you are familiar with MATLAB, you can use this mat file that includes like a large table matrix with all the data with the titled columns that identify what each column data represent, and you can use this to further process on your own independently the data to plot maybe some more bespoke or individual decision variables or plots of interest for your own project. So this can be done here as well, which gives more flexibility to the user.